So this first section, that's part of our review, is about numbers, different types of numbers, in fact. And we usually illustrate or position those numbers on an axis like this. For example, I could indicate the number 0 here, and then 1 here, 2, 3, 4. Okay, now those are what we call here the positive integers. Okay, and those positive integers are actually also called the natural numbers. Sometimes 0 is included in them, sometimes it's not used. So by definition it's not, but it's not a big problem if you're asked like what the natural numbers are and you start with 0. It's not a big deal. Then we have also negative numbers that seem somehow obvious to us, but in the past, not so long ago, I mean some did not agree that those numbers actually existed, and they were introduced way after the positive integers were introduced. But we could, for example, give meanings to those negative numbers, right? Saying like, let's say you owe someone $1, then your assets is -1, huh? And if you have $2, then your assets are equal to 2. So those are negative numbers. Okay, and 0 is important because it quantifies something that's empty, right? But also it's a very important number because it's also a placeholder. So, I don't know if you know a little bit about Roman numbers, but this is 1, this is 2, so 2, and then this is 3, and ultimately, we can keep counting. There are symbols. There's a symbol for 5, and this is actually 10. So you need a symbol for 10, but in our system, it's not like that. We've got the numbers 1, 2, 3, all the way to 9. And after that, we don't need more digits to... actually, we do. We need one more. We need the digit 0. But after that, we don't need more digits to create new numbers. Okay? For example, this is 10. And 10 is actually the digits 1 with the digit 0. And 0 is actually a placeholder here. It actually tells us that 1 is not the same one we have here. It's in a different position. And then... it means we have 10 units, okay? But if I put 2 zeros after the 1, then now the 1 stands for 100 units, okay? So the 0 is a very important, it's a placeholder, and was introduced by Indian mathematicians quite a while ago, and was discovered eventually by the Western civilization, but was used way before in India. Way before we actually used it. It was used in Europe. Okay, so it was brought back actually from in some way from India to the Western world. Okay, so those are some numbers, but we can actually tell on our axis that there are places where we don't have numbers yet. For example, is there a number right there? Okay, so we can add more numbers by looking at what we call rational numbers. So we've got two integers, m and n, and they're one's divided by the other. And this, when we have this is a rational number. Okay, and this is when m and n are integers. So we've got what, 1/2, that's a rational number, but we can also have like negative numbers like this, -7/3. Usually, we can write 7 over -3, but usually the minus is always brought either in the numerator, or we can also put it in front of the fraction. So these are two natural ways of writing the fraction -7/3. The symbol for that. Oh, I didn't actually tell you, but there are symbols for the sort of positive integers, which are the natural numbers. This is n. If we include all these, the 0, the positive integers, the negative, so I wrote numbers, but I meant integers. We've got the integers, plain and simple, integers. The symbol for those is Z. And the symbol for rational numbers is Q. Notice how we always put a little bar, so it's N like this. Whoops, not my best N. N like this, Z like that, and Q like this. Okay. Some of them, for example, 15/8, in decimal representation, well, the decimal representation is finite. It's a terminating decimal. We have terminating decimals. But for most, it's not like that. For example, 4/11, it's 4.363636. Notice how this 36 repeats itself. So the notation for repeating decimals, usually we put a bar on top of the decimals that repeat themselves over and over. So a lot of irrational numbers are like this. You've got repeating decimals. In some way, we could say there are repeating decimals here. You've got like 0 that repeats itself. Okay, so it actually could be a way of defining rational numbers, is to say that their decimal representation is such that there are always some digits that actually repeat themselves. Sometimes you've got part of the numbers that repeat themselves. So you see here, this 8 doesn't repeat itself. It's the 3s that actually do. So this would be written 0.83 repeated like that. Okay. And if you want to have fun, you could actually look at something like this and try to do long division to find the decimal representation of this. You see, you have to wait a long time before you find out how many, what's the pattern, like which actually decimals repeat themselves. So sometimes this could be a daunting task to do. So now it seems we've got all the numbers that will actually fill in this axis here, but in fact, that's not the case. There are still numbers that are missing. So some numbers are still missing. What kind? Well, think about this number. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13. That's a number, right? There's a pattern, but it doesn't repeat itself. Okay, you can actually tell what the next digits are going to be, but there's nothing repeating itself here. So it's not part of the rational numbers. You could have something like this, 1, and then followed by a 0 and another 1, and then 2 zeros and a 1, and then 3 zeros and a 1, then 4 zeros and a 1, and so on. Okay, there's still a pattern, but it doesn't repeat itself. You've got a number that's called pi. It's kind of famous. 3.1415926535, and you keep going like this. There's no pattern here. Okay, you won't find any. Another one that's kind of famous, root of 2. 1.4142135, blah blah blah. In fact, pretty much, well, not pretty much, but every square root of a number that's not a perfect square is going to be like that. You're going to have digits that actually don't repeat themselves. So here there's no repeating decimals here. Okay, so it seems that there aren't that many of those, but in fact this is maybe counterintuitive, but this is actually false. So this set is called Q prime. Prime is and set is the complement, or the complement of another set. So Q prime is whatever is not in Q. Okay. So in fact, even though I wrote Q here, all the numbers I've added here in Q, you can also add integers, right? For example, 1 is 1/1, 2 is 2/1. So those are also rational numbers. So all the naturals, the integers, they're rational numbers as well. And so anything that's not rational is called irrational. okay? And there are way more rationals than any other type of numbers, okay? There are more rational numbers than there are rational numbers. And when you, if you take the rational numbers and you add the irrational numbers, then you're going to be able to fill in every single part of that line that I drew here. Okay, so you're going to get, overall, that continuous line contains all the numbers, and we call them the real numbers. Okay, notice this R again with this, where you double the vertical line. So this is Q, and if you add Q prime, you get the set of real numbers. Like that, okay? So if this is R, this is 0. What you've got here are all the positive numbers. Here you've got the negative numbers. And if you want to include 0, like say the positive and 0, you're going to say, this is kind of strange, but this is how it's done in English. You see the non-negative numbers. So you actually, it's a negation of the other. The numbers are not in that set. Non-negative numbers. And then you've got the non-positive ones. Okay. Now maybe I'll just end by showing you that, you know, something that you may not have seen before, but I want to show you that there are, for example, just as many natural numbers as there are integers. That's kind of weird, right? You'll say, well, natural numbers are 1, 2, 3, 4, 5, and then for integers you have to include more, but both are actually infinite sets. So how do you compare infinite sets? You actually try to list the elements in that set. Okay, so 1, 2, 3, 4, 5, 6, those are all the natural numbers. Okay, and if I can actually have a list here with all the integers, okay, we're gonna say I have just as many natural numbers as I have integers. For example, here I could say 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4. So there's basically a one-to-one correspondence between numbers in the first list and numbers in the second list. So because of this, we can say that those two infinite sets are in size about the same. Okay, or actually we say they're exactly the same in size. Okay, and surprisingly, I can do the exact same thing with Q. Okay, there are just as many natural numbers using that same principle. Like I'm going to be able to list rational numbers, okay, one by one, just like I did for the natural numbers, which means that both sets actually have the same number of numbers. Now, to show you how this works, imagine I've got the Cartesian plane here in only the first quadrant, and when I'm looking at a point, let's say with coordinates a, b, so it could be, I don't know, 3, 4, let's say, okay, I'm going to associate to that number the number a over b. So if it's 3, 4, it would be 3 over 4. So for every dot that you see here, I can actually come up with what the rational number is. So this is here, right there, this is the point with coordinates 1, 1. So this is 1 over 1. So that in other words, it's 1. This one is 2 over 1, because the x-coordinate is 2. This is 3 over 1, in other words 3, 4 over 1, and so on. Here this is 1, 2, so this would be 1 over 2, so 1 half. This is 2 over 2. This is 3 over 2. Okay, and then this would be 4 over 2. This is 1/3. This is, oh, and one thing to notice is I have repetition, so those two numbers are the same, right? This is, the coordinates are 2, 3, so this is 2/3 right there. I don't have to, I have 3 1/2 and 2/3, so they're not the same. Then here I have, this is 3, 3, so I have 3 over 3. So once again, I've got repetition, right? 3 over 3 is the same as 1 over 1, which is the same as 2 over 2 also, okay, and so on. But you can see that by associating to each point like this rational number, I can have in the first quadrant all the rational numbers, right? If you give me your favorite number, say 7 over 4, well, it's going to occur at the point 74. Okay, so if I can actually come up with a list of all these points, I'm good. And the way we actually come up with this list is that we go about them this way, like this. You could kind of cover the diagonals here, like that. And then you keep going, okay? And then you'd go up here, and then you'd go down, and okay? And by doing this, I'm going to be able to come up with my list. So the first number is 1 over 1. I could just write 1, but I'm going to write 1 over 1. Then you've got, the next one is 2 over 1. So I'm basically going about the red bat. And then 1/2. Okay, after that, 1/3. And after that, 2 over 2. I'm going to skip that one because it's already on my list. And then I've got 3 over 1. And then 4 over 1. And then 3/2, and then 2/3, okay, and then what would be the next one? It would be 1/4, yes, 1/4, okay, and I'd keep going like this, and I could list all the rational numbers, and this way, I can see that I've got again a one-to-one correspondence between let's say numbers on the natural number list and numbers on my irrational number list. Okay, so there are just as many natural numbers as there are integers as there are irrational, but one thing that someone has proved is that I can't do this for q prime. Okay, can't do it. Can't do it. We can't do it because there are way more numbers. Okay, that list does not, I cannot come up with a list like that. So someone has shown you cannot create a list like that, like enumerating one after the other the irrational numbers. Okay, and in fact, you can say that on the interval 0, 1, if I just look at the interval 0, 1, right, there are more irrational numbers there than there are rational numbers throughout the entire line, or more irrational numbers than there are natural numbers. So this is what I just wrote here. So I picked 0, 1, but I could have picked any small interval. You can even pick like 0, 0, 0.1, and in that interval you'll find more irrational numbers there within that interval than there are rational numbers throughout the entire real line. Okay. And finally, I'll end up with a little graph, okay, of our set. So we've got what here. These are the natural numbers. You'll find what 1, 2, 3. You'll also find something like square root of 25 because that's just 5. Okay, and then you'll have the integers. So you'll have more. Yeah, that includes 0, -1, -2, -7, but also something like minus square root of 16 because that's -4. And then you've got rational numbers that include those as well. Okay. And then you'll find things like 8/3, but also something like 8 root 3 over root 3 because that simplifies to 8. 7 over 12. And then you'll have whatever is here, okay, that was not a rational number is an irrational number. And that set here are all the real numbers. And here you'll find a lot of numbers, like root 2, pi, root of any number that's not a perfect square would go. There's also a famous number called e that we're going to see later on in the course. And there are other numbers here too. We just won't see them. One of them is called I, and it stands for the square root of -1. So if you allow the square root of negative numbers, then you include you have numbers that are not part of the real numbers, but we won't see them in this course. So that's kind of an overview of the numbers we're going to be working with, we're mostly going to be working with real numbers.